Welcome to this next lecture on vibrations of plates and shells. We are in this topic of connected systems, okay, connected systems. And we are using the receptance method to connect the systems and find the new mode shapes and resonances. So we did one example, the simple example last time. So let us augment that example. There are two systems now. Attached or connected rather at 2 points. At 2 points. Okay. So we have system A again, point 1 on system A, point 2 on system A, and then system B, point 1 on system B, point 2 on system B, they are connected. So as before, there is a force FA2 here, FA2 e to the power j omega t, FA1 e to the power j omega t, and displacements for A and B. Okay. So what happens? For system A, alpha 11 is equal to XA1 by FA1. Response at 1 by force at 1 is alpha 1. Then we have alpha 12, which is response at 1 by force at 2. Okay. And we have alpha 21, which is response at 2 due to a force at 1. Then alpha 22, which is response at 2 by force at 2. Similarly, for system B, what do we have? We have beta 11 as XB1 by FB1 and beta 12 is equal to XB1 response at 1 by force at 2, harmonic force. Then beta 21 is equal to XB2 by FB1 and beta 22 is XB2 by FB2. Okay, these are the individual system receptances. Now they are connected. Okay, that is the whole point, they are connected now. Okay, when they get connected, whatever happens, displacements are same. It's a rigid connection. Displacements are same. And forces being internal, forces are internal. So they are opposed. Okay. So now see what happens. What now happens is, so within the individual systems, what is the response at xa1. Okay, xa1 is responding. So we have system A 0.1, 0.2, we have cut it off from system B, so there is FA1 and FA2. So what is the response here due to these two forces? Okay, what is the response here? There is a response here due to these two forces. Similarly, there is a response here due to these two forces. So what are those? So again, amplitude, if we take, because everything is at single harmonic frequency. So if we take the amplitude, it is equal to alpha 1 1 plus FA1 into FA1 plus alpha 1 2 F8. Okay, response at 1 due to a unit force at 1 multiplied by the force amplitude. Response at 1 divided by, for a unit force at 2 into force amplitude at 2. Okay. Similarly, what is XA2? XA2 is alpha 2 1 FA1 plus alpha 2 2 F8. Okay, what is this? Response at 2 for a unit force at 1 into the amplitude of the force at 1. Response at 2 for a unit force at 2 into the force at 2, amplitude of force at 2. Okay, it's a linear system. Then XB1 is equal to beta 1 1 FB1 plus beta 1 2 FB2, the same logic, and XB2 beta 2 1 FB1 plus beta 2 2 FB2. Okay, so here comes the connection. I said it a little early ahead. Here comes the fact that there is a connection between the two systems. Okay, so what is the connection? A1 and B1 are connected. So A1 and B1, they are connected. Okay, so XA1 will be equal to XB1 first of all. So what is that? Alpha 1 1 FA1 plus alpha 1 2 FA2 shall be equal to beta 1 1 FB1 plus beta 1 2 FB2. Similarly, alpha 2 1, 2 point is connected to 2 point. So XA2 is equal to XB2. So alpha 2 1 FA1 plus alpha 2 2 FA2 is equal to beta 2 1 FB1 plus beta 2 2 FB2. Okay. Now what? Now the forces here are internal. Okay. So FB1 is equal to minus FA1. And FB2 is equal to minus FA2. Same here. FB1 is minus FA1, FB2 is minus FA2. Okay. So what happens now? If I substitute minus FA1 minus FB2 here and here, and then we have FA1, FA1, FA2, FA2 and so on. So if we collect the terms, okay, so we have alpha 11 plus beta 11 FA1 plus alpha 12 plus beta 12 FA2 equal to 0, and alpha 21 plus beta 21 FA1 plus alpha 22 plus beta 22 FA2 equal to 0. If we now put it in a matrix form, have alpha 11 plus beta 11, alpha 12 plus beta 12, alpha 21 plus beta 21, alpha 22 plus beta 22, FA1 FA2 equal to 0. Okay. So now for non-trivial solution of A1 and A2, if this 0 has to hold, then this must be singular. That means its determinant is 0, and that gives the equation for new resonances. Okay, that is stage 1, new resonances. Okay, after we find the new resonances, we have to find the new mode shapes. That is the next step. Okay, so we will take one example. Okay, so we will take an example. Let's see. Example. Okay, so again it's a simply supported plate. And I will use a spring. Connection point is x1 y1, and there is another spring x2 y2. This spring is grounded. Okay. So now this plate is system A for us, and this 2 springs is system B for us. Okay. So now we have to find alpha 1 1, alpha 1 2, alpha 2 1, alpha 2 2 for system A, then beta 1 1, beta 1 2, beta 2 1, beta 2 2 for system B. Okay. So, without restarting the whole thing, the response, plate response to a point force okay. So, let us say point force at x1 y1, what is the plate response? W x comma y comma t is summation over m and n 4 by rho h a b, force amplitude modal force m pi x1 by a sin n pi y1 by b divided by omega square mn minus omega square, then the mode shape sin m pi x by a sin n pi y by b and harmonic. So, this is the response of the whole plate to a point force at x1 y1. Okay. Similarly, let us say 1. Similarly, response of the plate to a point force at 2, 4 by rho h a b f sin m pi x2 by a sin n pi y2 by b by here omega square mn minus omega square. Again mode shape sin m pi x by a sin n pi y by b e to the power j omega t. Okay. Now, from here what is alpha 1 1? Alpha 1 1. Okay. So, response at x1 y1 here due to a force at x1 y1 okay, and divided by the force and the harmonic term. So, this also becomes x1 y1. So, we get summation over mn 4 by rho h a b sin square m pi x1 by a sin square n pi y1 by b divided by omega square mn minus omega square. Then what is alpha response at 2 with a force at 1? Okay. Then this becomes x2 y2, right. So, then we have summation mn 4 by rho h a b sin m pi x1 by a sin m pi x2 by b sin n pi y1 by b x2 by a, and then lastly sin n pi y2 by b and the frequency omega mn square minus omega square. Okay. What is alpha 1 2? Response is at 1 due to force at 2. Okay. So, here this becomes 1 1. but that looks like 1 to 1. Okay, so 4 by rho h a b sine m pi x2 by a sine m pi x1 by a sine n pi y2 by b sine n pi y1 by b minus omega square. So these two are equal. So alpha ij is equal to alpha ji. This is Maxwell's reciprocity. Reciprocity. And lastly, what is alpha 22? Alpha 22 is force at 2, response at 2. 4 by rho h a b sine square m pi x2 by a sine square n pi y2 by b divided by omega square mn minus omega square. Okay, that is with respect to system A, which is the plate. What about system B, which has 2 springs? Okay, so if I say that this is point 1 and this is point 2, what is the spring response at 1 due to a force at 1? Beta 1 is 1 by k1. Let's say this spring is k1 and this spring is k2. Then what is beta 22? Response at 2 for a unit force at 2, which is 1 by k2. Then lastly, what is 1 2 and 2 1? The response, the springs are now disconnected from the plate. So if I apply a force at 2, what is the response here? 0. Okay, if I apply a force here, what is the response here? 0. So this is 0. Okay, so now how does this system look like? How does this system look like? That system looks like alpha 1 plus 1 by k1, alpha 1 alpha 2 alpha 2 plus 1 by k2 into fa1 fa2 equal to 0. Okay. So now the determinant of this, which is quite involved, okay, the determinant of this matrix will give you, when you set it to 0, the new natural frequencies. New natural frequencies. Okay. And also, let's say you have this plate over here. Okay. And suppose along some line I have arranged a bunch of springs, not just 2. Okay. I have arranged a bunch of springs. even more, let's say. One, 2, 3, 4, 5, 6, 7, 7. Then I will have a 7 by 7 matrix now. I will have a 7 by 7 matrix, and FA1, FA2, sorry, through FA7, that is equal to 0. And suppose I want to put a zero displacement constraint along this line. I do not want displacement along this line. Okay, I can set all the ki's to infinity. Then these terms will be going to 0. All the diagonal 1 by ki type terms, they will be going to 0. Okay, then what happens is this will approximate a zero displacement constraint along that line. Okay, in actuality, if you look at it, there will be some minor displacements happening between, but it will effectively be a line constraint along. Okay, the more springs you put, the more better you get, but okay. So you get a line constraint along that direction. Okay. Now, so the determinant gives the natural frequency, new natural frequency. But what about the new mode shape? New mode shape. Okay. What about the new mode shape? First of all, the response of the plate is a double sum force over rho h a b applied location x star by a sine n pi y star by b by omega mn square minus omega square into the mode shape sine m pi x by a sine n pi y by b e to the power j omega t. Okay. So now how to find the mode shape? How to find the mode shape? Okay. So now you have, let's say, 3 springs or 2 springs, whatever. We started with 2 springs. Okay, and suppose I found a new set of natural frequencies for the 2 spring connection, which are omega I, new, let's say, I going from 1, 2, 3, etc. Now, if I find omega 1 new and I substitute it in here, then the determinant goes to 0. Okay, and therefore I can find the non-trivial FA1, FA2 values. FA1, FA2 value, they are like the eigenvector for omega 1 nu. Okay, so that means what? I have a force, FA1 at one location, I have a force FA2 at 2 location. Okay. So if I substitute omega 1 nu here, okay, and find the response of the plate to a force FA1 at x1, and add it to the response due to FA2 at x2 y2, okay, W1 x comma y comma t plus W2 x comma y comma t. This is a response due to FA1, this is a response due to FA2 at omega 1 nu, and that is the new mode shell. It is the new mode shell. Okay. Of course, if you finally, as I said, take the k values to infinity, they will become supports. They will become supports. Okay. So, this is a powerful technique. Instead of linear springs, you can use rotational springs. Okay. Then you can put line receptance. Okay, you have a plate and you want to stiffen along an entire, dimension using a beam or something. You can do that using line receptance. Okay, you cannot do it if it's a part. Okay, if it's a part, you cannot do it using a line receptance. Okay, if it's along the entire dimension, then you can do it because this boundary condition is known. It's the same boundary condition as that of the plate, then it's doable. Okay, then you can have line moment connections. You have two plates, they are connected through rotation over here, over the entire edge. That can be done. Okay, or if you have a cylindrical shell, and you put a stiffener, that means you put a ring around it and stiffened it. Okay, you stiffen that shell all around. Then what happens is the n that the shell goes through, either cos n theta or sin n theta, must be the same for the ring. Okay, if that is so, you can do a connection between the two and you can stiffen the shell. So, we will look at stiffening of the shell in the next class, how to stiffen a shell using a ring, using receptance method. Okay, I will stop here. Thank you.